Hello, I'm going to be talking about the principles of mathematical induction. And I realize this is kind of dark right now, so I'll go ahead and switch to the whiteboard. And I'd like to just to stress that if we're going to be using the integers primarily, the positive integers, if you're looking for a video on induction of more general totally ordered sets, you probably are overqualified for this video. So let's get started. All right. And so let's just title this induction. And we'll start with the integers. Now the question is what is mathematical induction? Well, it turns out mathematical induction, which is used as a proof technique, is really just the least positive integer principle for integers in disguise. Now, typically speaking, this is how you actually use induction in a let's say in a math class or in an application or whatever. Let's say we'd like to show, let's say we want to show that 1 plus 2 plus 3, you add up the first n integers, and you get n plus 1 over 2. Let's say you'd like to show that. Well, the way you're usually taught to do that is you start off with what's known as an anchor statement. And I'll talk about this a little bit later. But the anchor statement says it's true for n equal 1, question mark. Is it? Well, let's see. 1 is equal to question 1 plus 1 over 2, and the answer is yes. So this is what's known as the anchor statement. Now I'll explain the logical reason for that in just a bit when we go over why induction works. The next thing you do is now you assume true for let's say n equal 1, 2, all the way up to some k. Now, I'll explain, if those of you who have heard of weak induction versus strong induction, well, I'll explain what's going on here just a bit. But you assume that the statement is true for up to some k. Then you want to show true for n equal k plus 1, provided these are all true. And of course, what you do is you'd say, okay, 1 plus 2 plus 3, all the way up to n plus 1. Well, by the induction hypothesis, this is just n plus 1. Because remember, we assume that the induction hypothesis, oops. So I just screwed that up, didn't I? Hopefully that won't lower your confidence in me too much. Then you add k plus 1, then doing a little bit of algebra, factor out a k plus 1, we get a k over 2 plus 1, factor out a 1/2, so we're going to have left with a k plus 2, which is in fact what we want to show, that if you plug in k plus 1 in here, which is of course k plus 1, k plus 1, plus 1. So that's how you use it practically. But the question I'd like to explore in this video is, why does this prove anything? Why is this a proof? And let's see what's going on here. Well, what's really going on with induction, and at least on the integers here, is induction is really the smallest positive integer axiom in disguise. Now, what that means, what the smallest positive integer axiom means is, and it's an axiom, if S is a collection, is a non-empty collection of positive integers, then S has a smallest element. And I mean by smallest, I mean in the usual human order, the way human beings order integers. Okay, so that's what this means. So when you have an induction thing like this, what's really going on is as follows. So what happens is that you let S be a collection of labeled statements. S1, S2, S3, and so forth. In our example, S1 is a statement that 1 is equal to 1 times 1 plus 1 over 2 was our example there. And the question is, if one of the statements is false, there has to be a first false statement. And that's a crux of inductions right here. If one of these statements is false, there has to be a first false statement. Okay. So what's going on is that the anchor statement in other words, this one right here shows S1 is not the first false one. So if there's a false statement, if the collection of false statements is non-empty, then it can't be the anchor one. So that's what the anchor one does. So then what happens next is you say, all right, because you proved the anchor statement, this means we can assume the first false statement is of the form S of k plus 1 for some k. And this might be 2 or whatever. So then what happens is showing S1, S2, all the way SK are, so if are true, then if these imply that SK plus 1 is true, the first false statement cannot exist. that's what's going on with induction. There's no place for the first false statement to be. Now, so basically that's what induction is. Induction is, again, the least positive integer statement for integers. And the anchor statement, of course, is necessary for that reason. Now, there's a couple of things I'd like to point out before we conclude this little video. The first thing is that the least element principle it doesn't apply to a lot of other familiar sets of numbers. For example, it does not apply to, say, the rationals in, let's say, 0, 1. And it's easy to see why. It's 0, 1 exclusive. So what, 0 is not a part of this and 1's not a part of that. And to see why, well, let's say let Q be in here. Then 1/2 Q is less than Q, and 1/2 Q is also in there. So you can't, the set of rationals in between here, even though they're countable, under the usual ordering, the ordering that's consistent with our algebra, the least element principle does not apply. That's the first thing. And the second thing is that if you choose to induct on, let's say, a index set where there are let's say limit ordinals. And what I mean by a limit ordinal is I mean a ordinal omega where omega has no, or omega is not equal to, let's say, k plus 1 for some k less than omega. For example, let's say you're talking about some abstract countable set. And let's say this is the first countable ordinal, omega naught or whatever. If you're doing that, and basically what that means is that you can't reach omega via a countable number of steps, the hypothesis needs to be re-anchored at every limit ordinal. So be careful with that. You know, induction, as we said, works for these sets that where the no least element, I mean, an existence of a least element holds. For something like this, you do have to worry about limit ordinals, but that's a more advanced topic. So thanks for watching.